We just looked at the attention mechanism. Now we shall look at transformers which are based on the attention mechanism. Most especially the paper Attention is All You Need. This paper developed by Ashish Vaswani, Noam Shazer, Nikki Palmer, Jacob Uskorderate, Leon Jones, Aidan Gomez, Lucas Kaiser, and Ilya Polusiskin. The dominant sequence prediction models are based on complex recurrent or convolutional neural networks, as the 1D convolution neural networks we have seen previously, and then the RNNs like the LSTMs, the GRUs, and then the basic RNNs that include an encoder and a decoder. The best performing models also connect the encoder and the decoder through an attention mechanism. We've just seen that. We propose a new simple network architecture, which is the transformer based solely on attention mechanisms. So for the first time, we are not going to include any RNNs. We are going to work solely with attention mechanisms, dispensing with the recurrence and convolutions entirely. So we are not going to take or make use of recurrence or convolutions. Now, those experiments on 2 machine translation tasks show these models to be superior in quality while being more parallelizable and requiring significantly less time to train. This model achieves 28.4 blue score on the WMT 2014 English to German translation task, improving over the existing best results, including ensembles, by over 2 blue score. On the WMT English to French translation task, our model establishes a new single model state-of-the-art blue score of 41.8 after training for 3.5 days on 8 GPUs, a small fraction of the training costs of the best models from the literature. So we shall see this in the literature shortly. We show that transformer generalizes well to other tasks by applying it successfully to English consistency parsing, both with large and limited training data. Now, RNNs, LSTMs, and GRUs have been firmly established as state-of-the-art approaches in sequence modeling, and transduction problems such as language modeling and machine translation. Attention mechanisms have become an integral part of compelling sequence modeling and transduction models in various tasks, allowing modeling of dependencies without regard to their distance in the input or output sequences. In all but a few cases, however, such attention mechanisms are used in conjunction with a recurrent network. Now recall how even though we had these attention blocks, we still used recurrent layers here for the encoder and also recurrent layers for the decoder. In this work, the authors propose the transformer network, which is a model architecture eschewing recurrence and instead relying entirely on an attention mechanism to draw global dependencies between input and output. The transformer allows for significantly more parallelization and can reach a new state-of-the-art in translation quality after being trained for as little as 12 hours on 8 P100 GPUs. Here we have the transformers model architecture. Now, the transformer, as many other translation models, have an encoder and a decoder. So this part is our encoder. So we have this encoder, and then this other part is our decoder. We also have the inputs and then the output right here, output probabilities, and then we have the shifted output. So this is actually teacher forcing, which has been implemented right here, because once we have the output, we shift this output and then insert it right here so that our model converges faster. We have the embeddings, which is what we used to already. We have the embeddings right here. We also have the embeddings. We have the positional encodings, which we shall discuss shortly. And then right here we know that this encoder is n times, and then the decoder appears also n times. So we repeat this n times and this other one n times. Now that schematic can be put as this, where we have an input, we have encoder layers which is stacked on each other. So we have this output which is input to this other one, and so on and so forth. We repeat this n times. We have also the decoder layer which is also repeated n times. And then if you notice these two inputs which get into this attention model here, this is actually the queries and the keys. So this output from the encoder which gets into the decoder is actually the output from the last encoder. So we get this output from the last encoder, we pass into to each and every one of the decoders. So we have something like this, so on and so forth. So we repeat this n times 2. Now let's look at the encoder in depth. The encoder is composed of n equals 6 identical layers. So in this paper, they choose n to be equal 6. And each layer has 2 sub layers. Now here are the 2 sub layers we're talking about. That is this multi-head attention, and then this feed forward layer or sub layer. Now the authors employ a ResNet kind of connection, that's a residual connection around each of the 2 sub layers. As we could see right here, we have this input which is passed into the sub layer, and that same input comes to be added with the output of the sub layer, and that's the same that's done right here. And then after this, we follow it with a layer normalization. That is, the output of each sub layer is passed into this layer norm function. So we have the layer norm of the input plus the output of the sub layer. So obviously the sub layer of the input will give you the output plus the input, which is there's a ResNet-like connection, and then we have the layer norm, where the sub layer of x is a function implemented by the sub layer itself. So here our sub layers are the self attention or the multi-head self attention and the feed forward network. To facilitate this residual connections, all sub layers in the model as well as the embedding layers produce outputs of dimension d model equals 512. So this is these are hyperparameters which we could always modify, but in practice we shall just use this. Now the feed forward layer is the kind of layer we've seen already. This in TensorFlow is the dense layer. Now for the multi-head attention layer, it's basically made of scaled dot product attention layers which have been running parallel. So this is just one scaled dot product attention layer, and then these are each of these attention layers which are being run in parallel. So when we get an input, we pass it through one of this, we pass it through the other, and so on and so forth. So we have this one, we have this other one, we have this other one, 8 different times. And then after this, we concatenate all these results and then pass it through a dense layer to obtain our output. Remember that our D model, or the output of the model, should have dimension D model, which we had seen to be 512. So that will be taken into consideration. Now, in order to better understand this, let's go in depth and understand the scaled dot product attention. Now, we call our particular attention the scaled dot product attention. The input consists of queries and keys of dimensions dk and values of dimensions dv. We compute the dot product of the queries and keys, divide as actually scaled by the square root of dk, and apply a softmax function to obtain the weights, that's the attention weights. Now if you notice, this is actually very similar to what we saw with the Badenau attention, with the difference that unlike the Badenau, where our similarity function was the additive function, here we're actually using the scaled dot product function, which is also called the Luong style. So you could check on that paper by Luong et al. To better understand this attention mechanism. Here is actually the paper in question. In practice, we compute the attention function on a set of queries simultaneously packed together into a matrix Q. The keys and values are also packed together into a matrix K or into matrices K and V. We compute the matrix of outputs as attention of Q, K, and V. That's attention which takes in the query, the key, and the values, and this equals the softmax of the dot product of the query and the keys. That's the scale dot product of the queries and the keys times the values. Now, this scale dot product is a similarity function we have seen, and recall also that x dot y, or for example q dot k, is the same as q times k transpose. Then we have the softmax, and then we find the context vector by multiplying this. So this looks similar to what we've seen already. The two most commonly used attention functions are the additive addition, that's the Badenau, and then the dot product. And specifically in this case, is we also have the scaling factor 1 on the square root of the key dimension. Additive attention computes a compatibility function using a feed-forward network with a single hidden layer. While the two are similar in theoretical complexity, dot product attention is much faster and more space efficient in practice, since it can be implemented using highly optimized matrix multiplication code. Now, for smaller values of decay, the two mechanisms perform similarly. Additive addition outperforms the dot product attention without scaling for larger values of decay. We suspect that for large values of decay, the dot products grow large in magnitude, pushing the softmax function into regions where it has extreme small gradients. To counteract these effects, we scale the dot product by 1 on the square root of decay, hence the need for the scaled dot product and not just the simple dot product. In the paper, we made mention of the self-attention. Now, let's look at attention previously described as or with this schematic. Now, for self-attention, we have these queries which are actually going to come from the same inputs. So supposing we had this, where we had the queries coming from the hidden states of the decoder, and then the keys and the values coming from the outputs of the encoder. Now, what we do here is we have this query, that's what gets into here is the queries. So we have these queries coming from the same encoder, and then we take this off from the decoder. So what happens now is the queries come from the encoder, the keys from the encoder, and the values too from the encoder. Then this now pass into this attention layer, which then produce the outputs. Hence we have the term self-attention. And as we can see now, each part of the input, that's from x1 to xl, each of them actually attend to each other. And then the attention weights we get after passing through the softmax layer will tell us how similar each of these is to the others. So here the attention is within the inputs, hence the term self-attention. We also note that right here we also have this, that is for this other query, this is taken off. We have this one is taken off, and this other one is taken off, since all the queries now are gotten from the inputs. Now in this our particular example, we'll see how we modified this. So this is no more the additive attention. Now here we have the scaled dot product attention, where we have this matrix multiplication of the query and the keys, or better still, the queries and the transpose of the keys. So we pass this in here, we have this matrix multiplication, the scaling, and then the softmax as we had with the additive. And then we also have the context vector calculation, and this too is also repeated. So we could take this off, we see how this goes away, this other one goes away, and we have this links now, or the queries which come directly from the input. Also note in the dimensions here that we have the byte size, we have 1, the hidden unit byte size 1, the hidden unit dimension, and this is repeated for the number of inputs we have. So if we have L inputs, this is going to be repeated L times. But we could always combine all this as one computation, and combining that gives us this, where we just have the queries. That's for we go through each part of the input. That's, for example, we have this, we break it up using 3 dense layers to generate the query, the queries, the keys, and then the values. Now we see that we have L different attention models or attention layers right here. Then for each of them, we pass in this query. You see the dimension batch size 1, hidden unit size, and then we now have all the queries, or rather all the keys and all the values which are passed in. So we have batch size L, which is this L right here, hidden dimension. So basically we're passing all this into this attention block right here. And then to make computation even more efficient, what we could do is to pass all this as 1. So instead of multiplying a separate query with the keys and then having to repeat that L different times, what we could do is we could stack all these queries into one matrix, one big matrix, which is this matrix of dimension batch size L and then hidden unit size. We now pass through the matrix multiplication, where we have the query times the transpose of the keys. We have the scaling, which maintains the dimensions, and then we pass through the softmax layer. After the softmax layer, we multiply the outputs of this, or the attention weights, with the values. Also note how this gives us right here the dimension of this tensor is batch size, the length L, and then L. So suppose we have L equals 5, we're gonna have an attention weight matrix like this for one of the batches. And so if we have the 5 inputs, say this is input 1, input 2, input 3, input 4, input 5, this value gives us a similarity between input 1 and itself, this the similarity between input 2 and itself, this for example gives us the similarity between input 3 and then input 2, this the similarity between input 4 and input 3, this the similarity between input 2 and input 4, and the same goes for the rest. So we've now understood perfectly the scale dot product attention, and let's now get into details of the multi-head attention. Now the multi-head basically is the scale dot product attention repeated many times. So instead of performing a single attention function with D-model dimensional keys, values, and queries, we found it beneficial to linearly project the queries, keys, and values each times with different learned linear projections to DK, DK, and DV. Actually, this is for cure, K, or the keys, and then the values, dimensions respectively. On each of these projected versions of the queries, keys, and values, we then perform the attention function in parallel, yielding DV dimensional output values. Then these are concatenated and once again projected, resulting in the final values as depicted in the figure above. So multi-head attention allows the model to jointly attend to information from different representation subspaces at different positions. And working with only a single attention head doesn't permit us get the different representations. Now writing this out, we have the multi-head, which takes in cure KVs, quite similar to what we had for the attention, is equals the concatenation of the different heads. So we'll call each and every one of those a head. So we have head 1 to head H times a weight matrix WO, where head I is attention of the query multiplied with a weight matrix W cure, the key multiplied with a weight matrix WK, and the values multiplied with a weight matrix WV. Now in this work, they use H, or they selected H to be equals 8, so we have 8 parallel attention layers or heads, and for each of these they used DK equals DV equals the D model divided by H, which is equals 64. Recall that D model was taken to be 512. 512 divided by 8 is 64. Now, due to the reduced dimension of each head, the total computational cost is similar to that of a single head attention with full dimensionality. So basically what the authors are saying here is, normally we have this cure with dimension byte size L D model, or the dimension of the model, which we could set, or which has been set to 512. Now, instead of passing for each of the heads or for each of the attention layers just cure, we pass now a modified version of cure, that's cure which has been projected. And this projection of cure actually has a new dimension. That new dimension is no more BLD model as cure, but is now BLDK for the particular example of cure. Because if we have the input, or if we have cure to be, for example, of dimension L, D model, then multiplying LD model with D model DK will give us LDK. So this cure W cure has dimensions LDK, and then KWK has dimension LDK, and then VWV has dimension LDV. So we aren't working no more with LD model, but now LDK, LDK, and then LDV. So the way these decays also have been selected is such that they are equals D model divided by H. So if we pass this input into our different heads, what gets into the head, like for example for this first one, suppose this H actually is equal to the D model, this H is the D model, and then NH in this case is 8, so the number of heads actually, so NH equals 8. So what happens right here is, for one of these, so suppose we have this input, we pass this in, for one of these we have dimension BL D model on NH, in this case it is 512 on 8, so we have 64. So we have BLDK, and then for this we also have BLDK, for this we have BLDK, for this we have BLDK, and for this BLDK. So we're supposing here we have the queries. If we pass in the keys and the values, is going to be similar to what we have for the queries. Now we're saying that once we have this outputs, for example, suppose we have this as inputs, once we have this as outputs, and that we concatenate this, we shall have an output of dimension BLH, because concatenating this NH times will give us BLH. If this was 64, having to add up this last dimensions together 8 times will give us 512. So that's how we have BLD model in the output. So we have input BLD model and then output BLD model. It's also important to note that since after concatenating this layer or this outputs, we obtain the dimension or a tensor of dimension by size, sequence length, and then the D model. It means that since the output dimension is the same as the input dimension, then we could easily have the ResNet like structure we have in the model, where we add up the inputs with the outputs as it's done right here. And so with that, we've understood exactly what's going on right here, where this linear layers actually are the projections. So we could use a dense layer in TensorFlow, and that would serve that purpose. We have the concatenate and we have another linear layer right here. So this has been understood. Now let's look at the applications of attention in our model. The transformer uses multi-head attention in 3 different ways. In the encoder-decoder attention layers, the queries come from the previous decoder layer, and the memory keys and the values come from the output of the encoder. This allows every position in the decoder to attend over all positions in the input sequence. This mimics the typical encoder-decoder attention mechanism in sequence-to-sequence models. Also, with the encoder, which contains self-attention layers, in a attention or in a self-attention layer, all of the keys, values, and queries come from the same place. In this case, the output of the previous layer in the encoder. So each position in the encoder can attend to all positions in the previous layer of the encoder. And similarly, we are going to see the decoder layer shortly, but there's the same or similar self-attention layer in the decoder, which allows each position in the decoder to attend to all positions in the decoder up to and including that position. Now we shall understand this, well, the concept of masking is going to come to play. So let's keep this for now and continue with this other parts. So we have the position-wise feed-forward networks, which are basically the kind of feed-forward networks we're used to working with. Now, in addition to attention sublayers, each of the layers in our encoder and decoder contains a fully connected feed-forward network, which is applied to each position separately and identically. This consists of two linear transformations with a ReLU activation in between. So look at this. For the very first one, that's this XW1 plus B1. This is the first layer. We pass now, or we have the ReLU. Recall the ReLU is the max between the output and 0. So if the output is negative, we're going to select 0. If the output is positive, we select the output. So this is that ReLU we're talking about here. Now that ReLU is passed into another layer, which is this plus B2. So but this other layer doesn't have or we don't use the ReLU activation in the second one. So for this feed forward network, we basically have this. Now, while the linear transformations are the same across different positions, they are different parameters from layer to layer. Another way of describing this is as two convolutions with kernel size 1. The dimensionality of input and output is D model equals 512, and the inner layer has dimensionality DFF equals 2048. So what we are going to have in here is we're going to have a dense layer in TensorFlow. We're going to have a dense layer with output 248. So we're going to have 248 hidden states or 248 outputs, because since we have 2, we're considering this as a hidden state. So we're going to have 248 or 2048 outputs, and then for the next or for the second feed forward layer, we're going to have an output with 512 neurons. So that's how we get that, and that corresponds to the dimension of the model. So now we've understood the encoder, and now we could look at the decoder. Now note that the decoder is very similar to what we had with the encoder, with just some slight differences. Here we have two attentions or two self attentions, where we have this first one, which is a masked multi-head attention with the same ResNet like structure. Here we have also the next one, which is exactly the same as this, a simple multi-head attention with a ResNet like structure. Then here again we have the feed forward network with a ResNet like structure. Let's look at the decoder. The decoder is also composed of a stack of n equals 6 identical layers. In addition to the 2 sub-layers in each encoder layer, the decoder inserts a top sub-layer which performs multi-head attention over the output of the encoder stack. Similar to the encoder, we employ residual connections around each of the sub-layers, followed by layer normalization. We also modify the self-attention sub-layer in the decoder stack to prevent positions from attending to subsequent positions. This masking, combined with the fact that the output embeddings are offset by 1 position, ensures that the predictions for position I can depend only on the known outputs at the position less than I. Now let's suppose we have this attention weights. So we have gotten an input, that's the decoder input right here, which gets in, and then let's say in this first decoder layer we have this attention weights. Then if we consider that decoder inputs are start token, M, L, apprentissage, and then approfondi, then while constructing the metrics we could have this, or we could say it like this, where this right here will represent the similarity between star token and star token. There's a similarity between star token and M. There's a similarity between star token and L, and so on and so forth. Then If you take this, the similarity between L and star token, between L and M, and so on and so forth. Now, given that we wanted the prediction at the first output, or the first output prediction should only depend on the first decoder input, and the second output should only depend on the first and the second decoder inputs. That's the second output should only depend on star token and M. The third should only depend on L, M, and star token. The fourth should only depend on apprentissage, L, M, and star token. And then the fifth can depend now on all. So we want to avoid a case where the output for M actually depends on approfondie, for example. So in that light, what is done is this similarities between all the rest of the tokens and star token, for example, are turned to negative infinity. And then for M, it's only M, or only star token and M which affect its value. For apprentissage, it's only apprentissage, L, M, and star token, and so on and so forth. So from this, we generate this new attention weight matrix, hence the term masking, because we are taking off a certain region. Then after passing this through a softmax unit, what we obtain now is this. So the negative infinity is turned out to 0. So we've masked this region out and we're left with this. So coming back to this, we had left previously, we need to prevent leftward information flow in the decoder. As we just saw, we want to prevent, for example, words that come up in the future to affect the output of words before that. And this is done to preserve the decoder's autoregressive property, which relies on the fact that the second value lies in the output. The first value of output depends on this, the next value depends on this, the next depends on this, the next depends on this, the next depends on this, and then the next will depend on this. Similarly to other sequence transduction models, the others use learned embeddings to convert the input tokens and output tokens to vectors of dimension D model. They also used usual learned linear transformation and softmax function to convert the decoder output to predicted next token probabilities. In the model, they share the same weight matrix between two embedding layers and pre-softmax linear transformation, similar to this paper. In the embedding layers, they multiply those weights by the square root of D model. Now, position encoding is also included in the transformer model. Reason being that the model contains no recurrence and no convolution, since it's an all attention model. So in order for the model to make use of the order of the sequence, the others inject some information about the relative or absolute position of the tokens in the sequence. To this end, they add positional encodings to the input embeddings at the bottoms of the encoder and decoder stacks, which is basically what we had seen here. So we have the embeddings, then we add this positional encodings for both for the encoder and for the decoder stacks. The positional encodings have the same dimension Z model as the embeddings, so that the two can be summed. There are many choices of positional encodings learned and fixed in this paper. In this work, they use the sine and cosine functions of different frequencies. PE, that is the positional encoding at a given position, and for an even dimension is given as the sine of the position divided by 1000, or rather 10,000 to the power of 2i divided by D model. And then PE for a given position, now for odd dimension, is the cosine of the post divided by 10,000 divided to the power of 2i divided by D model. Now this post is a position and I is a dimension. That is, each dimension of the positional encoding corresponds to a sinusoid. The wavelengths form a GP, that's a geometric progression from 2 pi to 10,000 times 2 pi. Now the authors chose this function because they hypothesized it would allow the model to easily learn to altern by relative positions, since for any fixed offset k, PE plus K can be represented as a linear function of PE post. And this is actually true because the sinusoids happen to be periodic functions. That's functions that actually repeat themselves after a given period. Now, after experimenting with learned positional embeddings, they discovered that they actually produce very similar results with this embeddings which were chosen right here. Then they finally chose this sinusoidal version because it may allow the model to extrapolate to sequence lengths longer than the ones encountered during training. Let's now take a deeper look of what is going on here. Suppose we have this embeddings right here, where we have the sequence length or embedding of dimension sequence length D model. So this make up each and every part of the sequence length, and then for the sequence length or for each part of this or for each time step we have this tensor of dimension D model, as we could see right here, or we could say this vector. Now what happens is we have, using this formula, we are able to generate another tensor which is similar to this embedding that we have here, this embedding matrix we have. Now the way this other matrix is generated, or this other tensor is generated, is in such a way that for PE, where we have a given position and then specified that our I is actually even, then we have the sign of the position, that is, supposing we have this position, for example, this first position right here. So if we have this position, then we'll take the sign of that position divided by 10,000 to the power of 2i. Now the I that we get here, since this is 2i, so it's practically, if we have an I here, then it's the same like this. Now the reason why we're working with 2i and then 2i plus 1 is just to tell you that this actually should be even. So if we start, supposing that we're starting from, like, this is the D model right here, so our i's go from, let's say, I equals 0, I1, I2, I3 up to D model. So when I is equals 0, for example, you'll find that we're going to be applying this or using this formula right here. Now when I equals 1, given that 1 is odd, we're going to be using this formula. When I equals 2, we're going to be using this formula, and so on and so forth. So we see how we actually move from, or we swap the different formulas depending on the value of I as we go on. And then the position, this post we have here, this position is simply where we're actually located in the sequence length. So the post is for the sequence length, and then the I is for the D model. Now this, once we have this, or once we're able to generate this, which is very clear now, so we take for each position we have the I, depending on whether the I is even or odd, we choose one of these formulas and then we put in the values, and that's fine. Then once we have all these values, so it's just like we're having some boxes we're trying to fill. So once we fill these boxes, we fill these boxes, we fill these boxes, and so on and so forth. We now have to add this two up. So to add this two up, this is now what we get. What we have now is this plus this, then this plus this, this plus that. So that's why I was stressed in the paper that we should have this positional encoding, which is the same dimension as that of the embedding, such that it could be added up together like this. So once we add this up together, we have now that output which is ready to be fed into the encoder or the decoder. Now in the paper it's also said that the wavelength goes from 2 pi to 10,000 times 2 pi. Now let's look at this function right here. We could define this as y equals the sine of 2 pi x divided by lambda, where lambda actually is the wavelength which was spoken of in the paper. Now the way we look at the wavelength is very simple. This sine function is actually a periodic function, so it's a function which repeats itself after a given or a certain period. Now if you notice, we have this first, and then it repeats again, and then repeats again, and so on and so forth. So the distance from one point to the next point, which actually looks identical to that same point, is what we call the wavelength. So from this to this, so if we fix ourselves to start at this point, you'll see that the next time we get to the same point is actually at this position. So this distance is the wavelength. Now if we fix ourselves, we start at this point, the next time we get to the same point is actually this, and then this x is some variable position. So once we understand this function, we see that we could compare this with what we had right here. Comparing this two, we have 2 pi x on lambda equals the position of this to the power of 2i on the model. Now solving for lambda, we have 2 pi times 10,000 to the power of 2i on the model. We're considering that the x and the pos are actually the same, so we canceling off that. So now we have 2 pi times 10,000 to the power of 2i on the model. Now let's suppose that we start with when I is equal to 0. So we'll start from the first position right here. When I is equal to 0, we have 2 pi times 10,000 to the power of 0, which is 1. So we start with 2 pi. Now when I equals 1, we see we go from that 2 pi to now 2 pi times 10,000 to the power of 0 again, because actually when I is odd, we take I minus 1, given that if we suppose an I is odd, in this case for example, where we have 2i plus 1, given that in this formula we leave from 2i plus 1 to 2i, it simply tells us that when I is odd, like in the case when I is equals 1, then right here we need to have 0 instead, so we have the same 2 pi again. If we move now to I equals 2, so we go to an even number, then we should be working with this, and then we should have the same 2. So here we're going to have 2 divided by the model, which now gives us a lambda of 2 pi times 10,000 to the power of 2 divided by d model. Now fast forward, we'll go from 0, 1, 2, and then finally to d model. Once we get to the position d model, we have d model divided by d model, which is 1. So we have 2 pi times 10,000 to the power of 1, which is 2 pi times 10,000. And that shows us how we leave from an initial 2 pi to now finally 2 pi times 10,000 as given in the paper. In the next section, the authors explain why they prefer the self-attention to the usual RNNs and conv layers. So in the section, they compare various aspects of self-attention layers to the recurrent and conv layers commonly used for mapping one variable length sequence of symbol representations, say x1 to xn, to another sequence of equal length z1 to zn, with xi, zi being an element of Rd. Now d could be taken as a dimension of the model, and then we have a sequence length of n, so each of this represents the whole sequence. Now, motivating the use of self-attention, they consider 3 needs. One is the total computational complexity per layer. Another is the amount of computation that can be parallelized. So this parallelization is very, very important, as it helps in speeding calculation when we have hardware like GPUs. So we have this as measured by the minimum number of sequential operations required. The third is a path length between long-range dependencies in the network. So note we have this second, and then we have this third. Learning long-range dependencies is a key challenge in many sequence transduction tests. One key factor affecting the ability to learn such dependencies is the length of the paths forward and backward signals have to traverse in the network. The shorter these paths between any combination of positions in the input and output sequences, the easier it is to learn long-range dependencies. Hence, we also compare the maximum path length between two input and output positions in the network composed of the different layer types. As noted in Table 1, here is the Table 1 in question. We have that the self-attention layer connects all positions with a constant number of sequentially executed operations, whereas a recurrent layer requires on sequential operations. So with the self-attention, we have this constant number of executed operations. When in the recurrent, we have big O of n sequential operations. In terms of computational complexity, self-attention layers are faster than recurrent layers when the sequence length n is smaller than the representation dimension d, which is most often the case with sentence representations used by state-of-art models and machine translation, such as word piece and by pair representations. To improve computational performance for tasks involving very long sentences, self-attention could be restricted to considering only a neighborhood of size R in the input sequence centered around the respective output position. This would increase the maximum path length to big O of n divided by R. They plan to investigate this approach further in future work. Let's understand how this ON squared times D comes about. To understand that, suppose we have instead Bn, because this is the sequence length right here. So in the paper, the supposed sequence length to be n. So suppose this is n, and then this h to be d. So here we have b and d. So it means at this point here we're gonna have b and d, and then the output will be b and n. So this matrix right here will be an n by n matrix, and the n square comes from the fact that we're working with an n by n matrix. Then the d also comes from the fact that we multiply this with this n by n matrix to get the context vector. Now, a single convolutional layer with kernel size k less than n doesn't connect all pairs of input and output positions. Doing so requires a stack of big O of n divided by k convolutional layers in the case of contiguous kernels, or big O of log n of k. So that's why we have this right here. Now, in the case of dilated convolutions, increasing the length of the longest path between any two positions in the network. Also, convolutional layers are generally more expensive than recurrent layers by a factor of k. Separable convolutions, however, decrease the complexity considerably to big O of k nd plus nd squared. And when k equals n, however, the complexity of a separable convolution is equal to the combination of a self-attention layer and a point-wise feed-forward layer, which happens to be the approach we take in our model. So the way self-attention works, or the complexity of a self-attention model, where we have the self-attention combined with the point-wise feed-forward layer, is similar to when we suppose k equals n for the separable convolutions. And as side benefit, self-attention could yield more interpretable models. And this is quite true, especially with the attention weights, which permits us to see exactly which of, or better still, which parts of the output actually are closely related to some parts of the inputs. We inspect attention distributions from our models and present and discuss examples in the appendix. Not only do individual attention heads clearly learn to perform different tasks, many appear to exhibit behavior related to the syntactic and semantic structure of the sentences. Now, coming back to this table, one very important feature of a self-attention model is that with self-attention, we instead have a big O of n squared d. And the fact that we have a big O of d right here makes it less computationally expensive working with self-attention models, since many times we have d actually greater than n. So if the parameter which counts the most when it comes to making our model very expensive is actually less eminent when it comes with a self-attention model, then it simply means that working with self-attention actually is a better choice. But also from here, clearly we see that when our sequence length is too large, such that it may even surpass d, then in such cases the self-attention models aren't the best models to use. Nonetheless, the authors propose this method where the self-attention could be restricted to a given neighborhood, such that instead of having n squared we have r by n, although now there's an increase in the maximum path length. From this we have the training, the optimizer, regularization, and then the results. It took 3.5 days on 8P100 GPUs, and even the base model surpasses all previously published models and ensembles at a fraction of the training cost of any of the competitive models. and we could check out the summary of these results on this table.